All right, welcome to This Explainer, brought to you by Forge College, where we are finally going to solve the incredibly painful mystery of shockingly high transaction fees and out-of-gas errors. I mean, we have literally all experienced that absolute moment of panic in Web3 development, right? You write a smart contract, everything is looking perfectly fine in your local environment, but the second you deploy it or a user actually interacts with it on-chain, the transaction abruptly fails. And to make matters worse, the associated cost report looks like a phone number. So today, we're taking a deep dive into the actual technical mechanics of gas on Ethereum-style virtual machines and compute units on Solana-style runtimes. We are going to look right under the hood to see exactly how your computational work is converted into a countable, payable measure.
Okay, let's quickly run through today's menu. We'll start by unpacking the mystery of unexpected cost spikes. Then we'll look inside the metering loop, introduce the restaurant tab mental model, check out the specific resource meters, diagnose a real execution trace, and finally, we'll cover pre-flight estimation.
So let's jump right into Section 1, the mystery cost spike. Or, why exactly did my quote-unquote simple transaction cost so much?
You know exactly what I'm talking about here. You submit what looks like a totally simple transaction, maybe just a basic token swap or a tiny variable update. The code is super elegant. But then, the receipt comes back showing this massive, inexplicable consumption of compute units. So why did this apparently simple transaction spike in price? Well, it's because the network literally does not care about your code's intent. It is only looking at every single micro-operation. It takes all these wildly diverse resource demands, like CPU cycles and disk storage, and forces them all into one single countable, payable measure.
Moving right along, Section 2, inside the metering loop. I actually like to call this the waiter's notepad.
Think of the metering loop literally like a waiter standing next to your table, aggressively tallying up your tab. They're constantly checking your budget limits and applying specific weights to every single opcode you execute. At the core of both gas and compute unit systems, this loop runs right in parallel with your instruction execution. For every opcode that fires, the runtime is updating its counters. It's ticking up an operation counter for the instructions, and then totally separate distinct counters for memory, stack, and storage access. Just imagine the runtime stepping through your opcode sequentially, ticking these counters up on every single tiny step. Then, when the execution finally finishes, all these different counters are aggregated together, multiplied by their specific weights, and transformed into that final, sometimes painful, cost invoice you see on your Block Explorer.
Which brings us perfectly to Section 3, the restaurant tab model. Appetizers versus premium entrees.
I love this analogy because it just makes so much sense. Just like dining out, your transaction can order cheap appetizers, things like basic arithmetic ops, or it can order premium entrees, like persistent storage rights. And those entrees come with a hefty surcharge for long-term state bloat. Think about it for a second. Computing a hash or doing some basic addition, that is incredibly fast and cheap for a network node. That's a basket of fries. But a persistent storage right, that means literally every node in the entire network now has to update its hard drive and store that data permanently. That right there is a dry-aged steak, and the network is absolutely going to charge you a massive premium for it. The metering loop is your waiter. You order the items as your code executes, and the waiter keeps a running total. And here is the kicker. If you try to order an extra expensive dish right as the kitchen is closing, meaning you hit the block or your transaction limit, you get stopped instantly. Bam! That is your out-of-gas abort.
All right, Section 4, resource meters and costs. Let's actually read this menu.
So let's look at the four main resource buckets the runtime is tracking. First up, opcode and instruction counts. This simply tracks your basic CPU-bound cost. Second, and this is a huge one, storage access. Reading and writing to persistent state. This drives long-term node costs, so it carries a massive unit weight. Third is memory and stack. If you're building giant temporary data structures, that pushes validator RAM up, which triggers really heavy costs. And finally, I/O syscalls. Think of these as your contract talking to the outside world, like external calls or cross-contract invocations. If you aren't paying close attention to these four specific categories, your code will just burn through funds like there's no tomorrow.
Let's see this in action. Section 5, Diagnosing an Execution Trace. The surprise surcharge.
Picture this trace unfolding. Everything starts off totally fine. You've got some cheap initialization ops. Then the transaction enters a dynamic loop. But suddenly, right in the middle of processing, the loop hits a hidden conditional branch. This branch forces the code to build a temporary data structure which causes a massive spike on the memory meter. And then, to make things worse, it writes that structure to persistent storage. Because the gas accounting system is strictly conservative, the runtime waiter checks the budget before executing the next expensive write, realizes your funds are insufficient, and boom, it throws the abort. You are officially out of gas. Now look at this trace. The trace reveals exactly 3 unexpected storage writes were enough to steepen the cost curve and completely exhaust the runtime budget. Just 3! Because storage accesses carry such an incredibly high weight compared to simple arithmetic opcodes, the combined effect of that memory spike and those 3 premium entrees completely blew the transaction's budget. It's a really stark reminder. It is rarely the thousands of simple math operations that kill your transaction. No, it is almost always the hidden, heavy storage or I/O calls.
So, how do we fix this? Well, you gotta change your order. Here are the direct developer fixes you need to apply. First, if you are doing multiple writes inside a loop, restructure it, period. Aggregate the data in memory, carefully of course, and perform one single compacted write at the very end. Second, if your memory is spiking, start using fixed-size buffers so your peak memory doesn't scale infinitely with user input. Third, if you have unavoidable external program calls, pull them out of the loop, do them once. And finally, if the job is just inherently too massive, you literally have to split the processing across multiple transactions to stay safely under those per-transaction ceilings.
Almost at the end here. Section 6, explaining pre-flight estimation. The pre-flight check.
Now you might be wondering, wait, why didn't the developers see this coming before they sent it? Well, this happens because an optimistic pre-flight estimate assumes the best-case scenario. Exact runtime metering, however, strictly enforces the actual live cost of those hidden loop branches. Think back to our restaurant. Pre-flight estimation is like asking the host for a rough quote before you sit down to eat. The node looks at the transaction, runs a quick heuristic simulation, and gives you a number. It assumes a standard, happy path execution. It didn't foresee that dynamic array triggering the hidden branch with the 3 extra storage writes. But exact runtime metering, that is the live, uncompromising waiter right at your table. It doesn't care about the estimate, it counts exactly what you consume, right in the moment. So when the runtime reality fails to match the optimistic estimator's assumptions, your transaction crashes mid-execution. By simply applying this mental model, you can now look at a trace, easily identify the expensive menu items, and optimize your code to keep costs low. Thanks for joining me on this explainer by Forge College. Make sure to head over to forge.college for more deep dives into Web3 technical concepts. But before you go, I want you to look at your own execution logs and ask yourself, are your smart contracts accidentally ordering way too many premium entrees?